Welcome, everyone. Thank you for joining us for the latest installment of our new Gleeble webinar series. Today's discussion will focus on recrystallization and Gleeble applications that support this important field of study. My name is Daniel Quigley. I'm the Director of Business Development and Marketing here at DSI. I've had the pleasure of meeting many of you already, either at your site or at conferences or trade shows. As you know, conferences are a great way for our team to connect with researchers like you to support your efforts and learn about the applications that are important to you. Unfortunately, our team, like much of the world, can't travel right now, so we have launched this webinar series to help us connect with you. As always, we know your time is valuable, so we appreciate you spending time with us, and we will strive to provide information that is relevant and impactful to you. Our goal will be to keep this webinar to 1 hour or less. If time allows, we will have Q&A at the end of the presentation. If you have questions, please submit them using the chat feature here in the webinar. We've got a number of members from the DSI team, including Brian Smahoski, Sean Garrity, Eric Dietz, and Brian Allen. They're all here with us virtually. And they may be able to answer questions directly in the chat during the presentation, or we may be able to address the questions during Q&A portion of the meeting, again, as time allows. We have been pleasantly surprised by the response to our webinar series. We have over 600 people registered to attend today. With this many people, we probably won't be able to address every question. However, we will do our best, and we will follow up after the webinar as needed. We want to be sure that we're covering topics that are important to you for future webinars. After this webinar ends, you will receive an email with a link to a short survey. Please fill it out and let us know what topics you are interested in. We will also follow up with a link to the presentation and a video, as well as any follow-up items that may be necessary. It's my pleasure to introduce our presenter, Dr. Fulvio Siciliano. For years, Fulvio has been helping DSI provide technical support to clients around the world. He's a well-known specialist in hot rolling of steels, mathematical modeling of hot deformation, recrystallization studies, and steel for oil and gas transmission pipelines. Fulvio has written textbooks and published about 100 technical papers that explore these research areas. We consider ourselves lucky to have such a talent on our team. Fulvio, I want to thank you for preparing this presentation, and I'll hand this over to you. The floor is yours.
Well, thank you very much, Dan, for this kind introduction. Hope you guys can hear me. Can you hear me?
We can hear you okay.
Okay, that's fine. So, well, thank you everyone for attending and spending your time to see this recrystallization webinar. Today there will be a very basic review of recrystallization and grain growth, and then we will focus on the possibilities that we have in a Gleeble platform to perform studies and simulations. So I'll be happy to interact with each of you and go deeper in the subjects that I cover very quickly here in this limited time, so that we can do that at the end of the presentation or offline after the presentation. So some of you will also be interested in more specific in rolling and TMCP. So I just want to tell that there will be another webinar focused on hot rolling and TMCP in the following 3 to 4 weeks, and it will be announced. So we can see that in our website. And well, I just want to start the presentation right now. And oops, sorry about that. Okay, so this is the outline. In the first part, I'll cover the basic principles of recrystallization and cover static recrystallization, dynamic recrystallization, and grain growth. And in the second part, we will see some possibilities in the Gleeble platform. So, well, recrystallization is known for at least more than 500 years. So this is not a new technology, and empirically, a lot of people knew that in the 1500s and even before that. So we can see that the first book of recrystallization of metallurgy, De la Pyrotechnia, from 1540. So Mr. Biringuccio made clear that, well, every time you were working on a piece of metal, he mentioned here gold, silver, and copper. So, and if it gets too hard, you should anneal it so it will get soft again. So this is basically recrystallization, and it was known independently of the dislocation theory that came well in early 1900s. So we can see that it's a work hardening or cold working is the oldest strengthening mechanism of metals, and increases hardness and strength. And probably the old blacksmiths, they knew that well before this publication. So this technology has been known for a long time. So this is not new, as you can see. In this overview, we see, well, in the upper part, I hope you can see my pointer here. So in the upper part, you see the changes in properties along the recrystallization process. And this is, let's say, schematic figures of the microstructures. So we have here the deformed state. We have a lot of defects, mainly dislocations. And this material, this metallic material, is hard and have a high strength. As we start the annealing process or increasing the temperature, we see that there is a decrease in strength and hardness, and this is due to the annihilation of the dislocations and forming and rearrangement of them, forming the subgrains. You can see the subgrains here inside the grains, and after that we have the nucleation and growth of the recrystallization process. So in this case, we have here a high angle grain boundary moving over the work hardened matrix, moving over the subgrains, and then you can see a deep decay of the mechanical properties and an increase of ductility and formability. So after the end of the process, we have the fully recrystallized microstructure full of grains and very low density of dislocations as opposed to this initial state. So you have a big decay in strength and hardness, and an increase in ductility. After that, if you keep the metal at temperature, the grain will grow. So this is basically to summarize. It's an overview to summarize the whole process. It's important to remark that all the energy spent to deform a metal, only about 10% is stored in the metal as dislocations and other defects. So, and this is actually the driving force for the recrystallization to occur. And this driving force for recrystallization is very low if you compare to other phase transformations. For example, copper solidification, we have 13,000 joule per mole. Solid state precipitation, 2,100 joule per mole, and a recrystallization of work hardened copper could be, let's say, from 10 to 50 joule per mole. So we see that there is an order of magnitude difference, and grain growth is even smaller. Well, we'll cover that. We'll cover these numbers later in this presentation. Why does recrystallization happen? This is an important question. We have in the work hardened state, due to the defects, we have a higher free energy, and the recrystallized state with very small amount of defects, we have a lower free energy. So if we give thermal conditions to that system, so the work hardened state will overcome this activation energy and will recrystallize. So this is a energy view of the recrystallization transformation. Now let's come to real life. A couple of pictures. This is austenitic stainless steel, deformed 50% in reduction, and annealed 800C for 3 hours. We can see here this on the left side. We see that the work hardened microstructure, and all the dark areas are dislocations. And we have the recrystallized grains, and they are growing over the deformed part of the specimen. Or in other words, when this grain here grows over this part of the microstructure, it will reduce the free energy because these dislocations will be eliminated. The same thing here. This is a tantalum metal deformed at 72% and annealed 900C for 30 minutes. We also can see this is the recrystallized grain with a very small quantity of defects. We can see, barely can see anything here, and it's growing over the subgrains. So in this case, we have subgrains formed, and this is because of the high stacking fault energy of tantalum as opposed to stainless steel. So this is basically what we can see when you look at the microscope. So that's what we see. This is a transmission electron microscope on the left and scanning electron microscope on the right. Well, the driving and dragging forces. Firstly, well, the driving force, the main driving force for recrystallization is the dislocations, and it can be calculated using this equation. Well, we've seen these equations a million times in papers and books, so I'd like to have some numbers to all these quantities. So this is the shear modulus, the Burgers vector, and the dislocation density, and we can have some numbers and some, well, an example. We have here this driving force for recrystallization due to the dislocations will be, let's say, 1,000 Newton per centimeter square. If you look at this unit, it looks like, well, it's a pressure unit. It's like to have, well, applying a pressure in the grain boundary to make it move. So actually pressurizes, or it pulls the grain boundary over the work hardened part of the system. So this is we can see here 1,000 Newton per centimeter square. Grain boundaries, the driving force for grain growth will be, well, we follow this formula, and this is the grain boundary energy, gamma, and this is the grain diameter. So this is a typical value for gamma in, let's say, in copper. And if you consider 20 micron grain size, so we have 5.3 Newton per centimeter square. So we see that, well, it's one order of magnitude lower than the dislocation density, than the driving force for recrystallization. We have also some dragging forces, or something that is preventing recrystallization to progress. And one will be the particle pinning. And this is the equation. This was derived probably in the 50s by 1949, I think, by Zinner. So this is the Zinner pinning, some people say. And this is, again, the grain boundary energy, the volume fraction of precipitates or particles, and the radius of the particles. Very interesting that if you move from, well, for the same volume fraction, if you have 5 micron particle of radius and then 5 nanometers, we see that there's a big difference in this dragging force. So this also prevents recrystallization to progress. And finally, the solid drag. We have here solid drag acting in the grain boundary. And well, it's a kind of complex, because you can treat solid atoms as particles in the beginning, but the only difference is that they can follow the grain boundary by diffusion. So I think this is the best way to explain that. At low grain boundary velocities, for example, grain growth, there's a small driving force, and so the grain boundaries, they move slowly. So the solid atoms, they can actually follow the grain boundary by diffusion. On the other hand, at very high velocities, let's say dynamic recrystallization, that it happens at very high speed. So the grain boundaries, they almost ignore the solid atoms in the grain boundary. And I think the highest effect is on static recrystallization. So this is on the peak. Of course, there's a very complex formulation for that. I have many papers. If you guys are interested, let me know. I can mail you the classic papers on solid drag. So let's cover like that. Well, let's stop here for now. Well, regarding the kinetics, how fast recrystallization happens, it actually follows a sigmoidal curve or S curve, or the Kolmogorov, Avrami, Johnson, and Mel. So the researchers that in the past got derived this equation and modeled this equation. So Kolmogorov, the Russian researcher, was the first one, followed by Avrami and Johnson and Mel. Johnson and Mel made the most didactic derivation of the sigmoidal curve, and this is the equation due to Johnson and Mel. So basically, you have the fraction recrystallized here and the time. We can see that there is a, well, in the beginning it's very slow and then increases this velocity, and well, at some point when the grains, the growing grains started to touch each other, so the speed decreases slowly. And so we can see here that, well, we have a 12 degrees C difference, and the time to complete recrystallization here, this is aluminum, okay? It's 8 seconds, and if you decrease for 12 degrees, well, it completes the recrystallization in 30 seconds. So we see that there's a strong effect of temperature, and the temperature actually is not included in this equation here, but it influences the growth rate, that is this G, and this is the nucleation rate, and this is the time. And this is the simplified version of the same equation. So usually when you're modeling, when you're deriving this parameter, you use this shape. Most of the time you don't consider all this, the growth rate and nucleation rate. So you add all that in this parameter here, A. So we may come back to that and how to include the temperature in the kinetics equation. So when the formation temperature is higher than 0.6 of the melting temperature, then we have we consider that we're having hot deformation. So I'm sorry for the Portuguese words. This original figure from a publication from McQueen and Jonas in 1975. I don't have a digital version, so I got that from my recrystallization book that is in Portuguese. But well, very simple. We can see it's self-explicative. So let's see that the first case we have rolling or a low deformation or medium deformation, 50% reduction in this pass. Again in this pass, and here you have extrusion, 99% reduction, area reduction. So in the upper case, in rolling, we have a high stacking fault energy metal, let's say aluminum, where the recovery happens very fast. So in this way, we see that, well, we have in the deformation zone, we create some dislocations and we don't have any new grains generated. So there is no recrystallization because the rate of recovery is very fast and it decreases the driving force for recrystallization. So in this way, we see here that there is no grain boundary move, just the grains are elongated, and we have softening by a dynamic recovery in the deformation zone and static recovery after unloading. If we have a low stacking fault energy, let's say austenite, we have a deformation here, creation of dislocation and driving force, and during the interpass time after unloading, we have the nucleation and growth of statically recrystallized grains. So if you go to a very high deformation in extrusion, in a high stacking fault energy, so the deformation is so high, so we create so many dislocations and driving force here that we have in a high stacking fault energy metal, like aluminum, we have static recrystallization in the after the deformation. And if we have low stacking fault energy, so we start having the recrystallization in the deformation zone. So this is dynamic recrystallization, and we will follow during the interpass time as metadynamic recrystallization. So this is basically a summary of what can happen when we do a hot deformation in a metal. We can see here metadynamic recrystallization, or it's a very simple concept. We have here strain accumulation in the passes, and at a certain time, well, the accumulated strain is so high that we nucleate dynamic recrystallized grains in the deformation zone, and they grow as static recrystallization outside the deformation zone. So this is metadynamic or post dynamic recrystallization. So we have dynamic here inside and post-dynamic after that. So I think this is it's a very clear concept, no big deal. Well, just to finalize this first part, again, I want to remark that recrystallization is not a new science. It's a very old science, as we saw in in the 1500s, and in the 1952, Burke and Turnbull, they formulated the laws of recrystallization, and this basically summarizes everything we need to know to use recrystallization in an industrial process or to study recrystallization for doing research. Basically, this is the main laws that includes static recrystallization. We have also some annealing temperature. Well, okay, the degree. No, we have one of them is says about the temperature of deformation temperature. Okay, yeah, I look for that later on, but also it includes the grain growth here in the last one. So this basically summarizes everything. So now I'd like to to show how Gleeble can be of a great advantage to study recrystallization. We have a few points to consider. Well, firstly, that it's a fast and reliable method to perform heat treatment. So it's very easy to use, very easy to mount a specimen, and to start a test and to program the machine. I think one of the most important is very reliable, and there's an accurate data recording, very precisely recorded. So we can have several temperature measurements in different positions of the specimen and so on. And I think one of the, maybe the most important, is that due to Gleeble system uses resistance heating, we have a uniform temperature profile. So this is a very important in recrystallization studies. And the reason is, we have here, let's say this is a cross-sectional area of a specimen, and this is the resistance heating, and this would be, let's say, furnace and induction heating. So in furnace induction heating, we start heating the surface, and then after soaking, it reaches the center of the specimen. So at a lot of occasions, you have the specimen with this gradient for a long time. So we see here that it's hotter here than in the center, that you have this dark yellow. And let's think that we have, let's say, 20 degrees difference in temperature from the surface to the center of the specimen. So let's come back here to this figure. You see how is the effect of just 12 degrees on the recrystallization kinetics. We can easily have a gradient higher than 20, 30 degrees when you heat a specimen with in a different method than resistance heating. That is uniform across in the cross-sectional area of the specimen. So it's very easy to see that this has a remarkable effect on the rate of recrystallization and on the kinetics of recrystallization. So I think this is one of the main points that Gleeble is. It's very useful, and it's a suitable method to study recrystallization, and besides being very reliable and accurate. So I'd like to give some ideas. Yeah, I have this figure again. We can study the effect of time and temperature on the recrystallization evolution, and the time and temperature on recrystallization grain size. So it's a very simple experiment. Okay, so I have a work hardened specimen, and I put that, I mount that into the Gleeble, and then I program this time, let's say 1.5 seconds at this temperature, and then this time again at this temperature, and several times. And I take all the specimens, I go to the lab, I mount the specimen, I grind, polish, etch, look at the microscope and do the quantitative metallography, and then I see how much is the recrystallized fraction. So I have the first curve. So this is a very simple heat treatment. I think the advantage of using the Gleeble is that you have uniform temperature across the cross section of the specimen. So you can rely on what you see in the microscope. So if you see close to the surface of the specimen, you can see a different microstructure as compared to the center of the specimen. It doesn't happen at the Gleeble. So the same thing can be done. No, this is a time consuming, of course, but well, at least you can generate this this microstructures at the Gleeble. And not only the recrystallized fraction to check the kinetics, but you can also measure the grain size. So you know the grain size and the static recrystallization evolution. Another point that you can study is the effect of the heating rate on high and low stacking fault energy metals, and also estimate the competition between recovery and recrystallization. These two factors are very important in the industrial processing. And well, just as an example, this is a low stacking fault energy metal. This is the stainless steel, and we know that recovery happens very slowly in the deformed zone, so it will not lose the driving force. So you keep the driving force and you keep the recrystallization progressing. If you have aluminum, for example, we have a very high degree of recovery in these deformed areas, and this might reduce the driving force for recrystallization. So it will slow down the recrystallization with time. And this is another way to see this effect. We have the percent recrystallized and the fractional softening. We can see that in low stacking fault energy, like copper, one corresponds to the other. But in aluminum, that is high stacking fault energy metal, we see that the softening happens much faster than the recrystallization, because there's a lot of softening by recovery happening in these deformed areas. So this is also can be studied with very simple heat treatments at the Gleeble. Regarding grain growth, we have again the grain size and the time and the curves for different temperatures. So we can study the grain growth also by performing discrete heat treatments at the Gleeble and evaluating the grain size with the specimen that you produce. So again, this equation and this theory is 1948. Again, just want to show again that this is very very old, but very useful. So this is an example of the time temperature graph for static recrystallization on grain growth experiment, where we have a ramp to temperature and then time at temperature, and then we interrupt the annealing by quenching or just turn off the heat. So this is a very simple experiment to produce reliable and uniform and reproducible recrystallized samples. So I want to show now grain growth. We show the curve, well, that graph for normal grain growth. Now this is a picture of abnormal grain growth, and this should be avoided in let's say engineering materials, because it reduces drastically the toughness of the steel or of the metal. So if you have these big differences in grain sizes, so this abnormal grains and normal grains here, there's a very deleterious effect on mechanical properties. So there's three ways that this abnormal grains can be formed, and one is the partial dissolution of precipitates in some certain areas. So certain areas we have the dissolution of precipitates, and then so the grain boundaries that were pinned by the precipitates at certain time they got free to move, and then they move faster than the other grains, and they grow faster in absorbing the normal or small grains. So this is basically the most common way to generate abnormal grain growth and form this big grains in the microstructure. So as a frequency analysis here, we have here the time and the grain diameter. So we start from a normal distribution of grain sizes. This is after you have a partial dissolution of precipitates, we have this bimodal distribution of grain sizes where you have the normal grains here and you have very big grains here. This is the abnormal grains. At the end of the process, we have only abnormal grains. So this is a disaster for mechanical properties, right? So how we can study that? Well, one of the possibilities, well, of course, we have to study case by case and why the abnormal grain growth is happening. But well, usually it's associated with high heating rates, because in high heating rates, you have a higher probability to have this partial dissolution of precipitates in in certain areas, and then this will generate the abnormal grain growth. So we can check. You can go to heating rates higher and higher. As you may know, Gleeble can go to 10,000 degrees C per second. This is the maximum we can go, and we can see how this high heating rates can trigger the abnormal grain growth. So we test the different heating rates and check what happens. So this is another example. I mentioned this is again, let's say the hot deformation. We have static and dynamic recrystallization studies, and this is the sigmoidal curve equation as derived by Kolmogorov, Avrami, Johnson, and Mel. And we can see here a new term. Instead of time, we have time divided by the time for 50% recrystallization. And the first time I saw that, I asked it to my supervisor, say, hey, why you have to introduce a new parameter here if you already have the time here? And then he said, oh, what about the processing parameters? We want to correlate the recrystallization kinetics with the processing parameters that we are preparing or processing our steel or our copper or our aluminum at the plant. So it's easy to derive by performing mechanical testing the time for 50% recrystallization or 50% softening. We consider for austenite that they will be equivalent. And this time for 50% softening, it will be, well, proportional to the strain, the Zener-Holloman parameter, or the strain rate corrected by temperature, the initial grain size. This is the activation energy for static recrystallization, the gas constant, and again, the temperature. So we have a way to derive the T50 and correlate that with the actual processing parameters or actual experimental parameters. So that's why this became very popular to use the sigmoidal curve equation at this form. So at the Gleeble, we can study, we can understand which softening mechanism is operating. We can measure the softening between passes. We can see the resulting grain sizes of that, and also we can perform hot rolling simulations. So let's, well, first thing, which mechanism is operating? We see that in a simple stress strain curve at high temperature, at a very high strain, we can see that there's a work hardening curve, there's a dynamic recovery curve, and it gets a flat plateau here because there is no grain boundary move, so there is no massive elimination of dislocations due to recovery. Recovery, it's a slow process. So when you see a peak, then we see that there is a dynamic recrystallization occurring in our experiment, and this peak, this decrease in tension, it's because there is a massive elimination of defects and dislocations. So the stress falls, and we see this peak and then a plateau. That's the steady state of dynamic recrystallization. And this is the peak strain and the critical strain. When dynamic recrystallization starts, is somewhere here. So we can see that there's a departure from this curve of dynamic recovery. So we can actually see that, well, we call that metallography by mechanical testing, but we can associate what we see in the mechanical test with, let's say, the microstructure and what's going on during the test. So something that we can also evaluate is the softening between two deformations, or could be two passes if you're simulating a rolling schedule. So how we do that, we have the stress strain curve, okay, without interruption. This is the black line, and we can stop the first deformation at a certain point, wait for the interpass time, and then reload the specimen. So we reload that. So if we do that, well, if you don't do anything, we just continue the curve. So we follow this black line. If we unload and wait for just 1 second, and then we reload by this equation, you can calculate the softening or the fractional softening in percentage. So this will be 2% softening, right? And you can see that the softening is when this part of the curve goes down. So it starts from a lower level as compared to the black curve. So if we wait 5 seconds, we have 30% softening. If you wait 100 seconds, we have almost 100% softening. So this is a way we can measure the softening between passes. This is very important in hot rolling because we know what kind of load to expect in the next pass. Extremely important. Also, we can estimate the grain size, and by doing different deformation schedules. We see here several passes with small deformations at constant temperature, and then fewer passes with high deformation in the beginning at high temperatures, and then lowering the temperature, increasing the stress, and having lower deformations at the end. Or we have these two big deformations in the beginning and 3 small, or 3 small in the beginning and 2 big. So we can test all these crazy rolling schedules, and at the end you can get a sample and specimen and measure the grain size. So we see that there's a big difference. So this is a typical industrial deformation process. We see that we reach the smallest grain size. And well, as opposed to this is not usual. Sometimes let's say in the forging process, you may get something like that, but usually not. Another example is the continuous annealing line. I think most of you are familiar with continuous annealing line. This is a monster equipment, almost impossible to stop. It's a continuous process. You don't want to stop that because it represents a lot of production time lost, and also a lot of material loss, because maybe there's almost 1 kilometer of strip inside this line. So of course you don't want to sacrifice all this big amount of material, and you want to understand what's going on, so you can calibrate your heating or thermal cycles, both heating, soaking, and cooling zones. This should be tested and calibrated, but offline, not in the line, because the line will be, let's say, a production disaster. So what we do, you can use a Gleeble, a large sample strip annealing mobile conversion unit, and test a sample. It's a quite big sample that we can test and run the exact thermal cycle that we have, that we plan, or that we want to improve in the continuous annealing line. But we have a very large uniform temperature zone here in this specimen, so we can do, let's say, a whole expansion test. You can stamp a tensile sample here in this big sample, and at the same time following the exact heating cycle or thermal cycle that you have in the continuous annealing line. So you have information about the microstructure and also mechanical properties by running the test offline and avoiding a huge experimental cost to understand what's going on in the actual line. So this is another very important use of the Gleeble. Of course, we have a work-hardened ferrite. Most of the time we have a work-hardened material or a deformed coil, and we have a recrystallization happen in the first plateau. And after that, of course, depending on the cooling cycle, you have the formation of the phases that you want to form. Finally, I'd like to show some example of the LUMAT. It's a laser ultrasonics to study microstructure. So it's a very interesting system. I'd like to show very quickly how it works. So we have here metallurgical samples. We can see here the grains, of course, are exaggerated in size. So there is a laser beam, a high power laser beam hitting the specimen and generating inside this ultrasound wave. So this ultrasound wave is later analyzed, and we have a graph of the amplitude of the wave and the time. We see here that this distance from the generation to the first echo is it's smaller than this distance for the second echo and is smaller than for the third echo. So this means that it's losing velocity and also losing amplitude. So there is a correlation. There is a software that correlates this two, the amplitude and the velocity of the wave with the metallurgical state of the sample. So just as an example, we can correlate the velocity of the wave and the time, and we see how this is correlated to different stages of recrystallization. So this is a deformed state, there's a low velocity, this is a partially recrystallized state, and then the velocity increases, and at the end of the recrystallization, velocity increases even higher. We can, of course, it needs some calibration at the beginning, but you can imagine how to generate, how to see that in real time during a hot deformation test. So this is what saves days or weeks of metallographic studies in the laboratory. So with just one sample, in a few minutes, you can generate, you can know exactly what's going on in your specimen in real time during the test. So this is the beauty of the LUMAT. I just want to show another example. This was originally made to study reheating of steel slabs. Okay, we have here this 3 points are microstructure generated by metallographic samples, and we have here 2 examples. This is the grain size and the temperature. So we see that in this first case, we have a very good correlation of the LUMAT points that measure the grain size in real time and the metallographic sample. Of course, this sample is different from this sample and is different from this sample because they have to be quenched and taken to the lab and get mounted, grinded, polished, etched, go to the microscope and do quantitative metallography. So it's a lot of time consumed to perform this test. And with the LUMAT, we have an excellent correlation with just one specimen. So at real time, we can just keep increasing the temperature and measuring the grain size. We can generate hundreds of points that might take weeks to do that manually. So this is another application for recrystallization and grain growth for the LUMAT. So I think that's the end of the presentation. We show a summary of recrystallization at low temperatures and high temperatures, and also grain growth. And a summary of the microstructural changes and how this can be studied and researched at the Gleeble. I just want to do a pre-announcement of the next one of the next webinars. We'll focus on TMCP, hot rolling, hot deformation, and high temperature recrystallization. And I try to cover firstly continuous casting and let's say items like ductility during casting. And this is I just add the short video, just coming back to my roots. The other day, I found the old pasta machine from my grandmother. Oh, it doesn't work. Yeah, let's see if it works now. Yeah. So this is my grandmother's pasta machine, and a week ago I decided to make pasta. So we will discuss hot rolling, and we can see some plates here in the cooling bed after rolling. And after that, we will show what we see during the the cooling stage. So thank you very much. Appreciate your time. And so I think we have a few minutes for questions. Let me know if it can be useful. Yeah, thank you very much.
Thank you, Fulvio. Great job. Very interesting presentation, and ended with some graphics to make us all hungry. Appreciate it. As I mentioned, we have a large group of attendees today, so there's been a lot of great questions. They were mostly submitted through the chat room. We won't be able to get to them all. However, we'll select a few of them, a few of the popular themes, and we can dive into them for more discussion. We may combine some of the questions and maybe paraphrase. And actually, we also have Dr. Brian Allen is available. So Fulvio, maybe you can catch your breath and we can direct a question to Brian as well. The first question is, it says that the TNR parameter has been used in almost every research related to SRX. In some papers, researchers consider 50% recrystallization for TNR, and in some it is considered as 40%. Is there any specific value of percent recrystallization to be considered for TNR determination?
Yeah, let me cover that. We can use 20%, we can use 50%, we can use 70%. The reason to use 50% is that it's easier to reach 50%. It's not, let's say, the very beginning. If you say it's 5%, 5% is it's more difficult to catch that in a microstructure. So, but 50, everything that you have to change from 50% is this parameter here, because this is the natural logarithm of, I have the exact formula here. Let me check. I have my my thesis printed here. So this is this constant here is because it's 50%. If it's 20%, we just change this constant, but it will have the same effect. Well, I'll find that sometime. Perhaps we can get to that later. But this kinetics equation, well, this constant is due to the 50%. Okay, if you use 20%, you have a different constant.
Okay, thank you.
Next question
is how is recrystallization affected by segregation of a phase from solid solution to the grain boundaries? Will it slow recrystallization or shift the temperature?
I'm sorry, can you repeat the question then?
Sure. How is recrystallization affected by segregation of a phase from solid solution to the grain boundaries? Will it slow recrystallization or shift the temperature?
Well, usually, as a rule of thumb, as you increase the level of solids or impurities, you decrease the velocity of the grain boundaries. So the recrystallization will be affected because the kinetics will slow down as we have more impurities. For example, let's get a practical example. If you have pure aluminum, let's say 5 nines aluminum, very pure, it recrystallizes below below ambient temperature or at ambient temperature. Also, metals like lead, there's a dynamic recrystallization at ambient temperature if the form. So, but this is for pure metals. As you add impurities, the recrystallization temperature starts to increase and the kinetics start to become lower.
Okay, thank you.
All right. Yeah.
Next question, it says, you have shown an example of simulation of the continuous annealing line. Can you describe how Gleeble experiments can be used to study batch annealing of steel coils?
Right.
And actually, Brian Allen also, I think, may have prepared an answer for that already.
Oh, yeah. Go ahead, Brian.
Yes, the Gleeble obviously has a good thermal control, so you can simulate essentially any annealing process that you would like. So you can use a Gleeble to simulate the batch annealing process of a steel coil. Now, the difference between batch annealing and continuous annealing is usually that in a batch annealing process, you're putting the entire coil in a furnace. So you have actually very different thermal profiles that occur in a coil in a batch annealing furnace, whether you're on the outer lap or the inner lap. So as you heat up as you place the coil in the furnace and heat the furnace up, the outer laps, of course, on the OD of the coil, as well as the inner laps on the ID of the coil are going to heat fastest. And then they're going to achieve temperature first. And then conversely, when you switch from the heating phase to the cooling phase of the batch annealing cycle, those are going to cool fastest and the center is going to be hottest. So it's easy enough to understand what those temperature profiles are by embedding thermocouples in a coil. And you can certainly simulate that in a Gleeble by just running a thermal simulation test that matches what you expect to happen in your actual coil. But I would just note that you're probably going to need a couple of simulations to actually simulate what happens in a batch annealed coil, because there are different temperature profiles, you know, in the center of the bulk of the coil versus the ID or OD laps of the coil. People typically don't use a Gleeble to simulate batch annealing because the batch annealing is a long process, you know, 24, 30 hours. And often people have other work on their Gleeble. They don't want to tie the Gleeble up for that period of time, but it certainly can be useful for that.
Great. Thanks, Brian. We have a question here that says, besides studying heating rate effect on abnormal grain growth, which other experiments could identify abnormal grain growth causes on a Gleeble machine?
The abnormal grain growth can be caused by, well, firstly, the difference in surface texture or the surface tension in different grain orientations. But the most common cause is the partial dissolution of precipitates. We cannot let's say, do a partial dissolution experiment a specific partial dissolution experiment in a Gleeble, but we can study, let's say, a process parameter that is the heating rate. So for high heating rates, usually you have a higher probability that this partial dissolution of precipitates will happen, and then at a certain point we will generate a very big grain size, and this will turn to be a bimodal distribution of grains that is very bad for mechanical properties. So we can actually simulate the exact parameters you have in a heat treatment plant or in an annealing cycle in industry, right? Or at the lab. So you can simulate several conditions at the Gleeble and find out which conditions are generating the abnormal grains.
Thank you. We had a question come in, and this is, I think it's a good question. I think if you ask metallurgists at DSI, they may get conflicting answers. So I'll put Brian and Fulvio on the spot here. But the question comes in, says, what is DSI view on the differences between uniaxial, plane strain, and torsion? Academics use a range of these and each have benefits. Has DSI done a cross comparison as Gleeble is capable of doing all these modes? It would be useful for a cross comparison. And this is, again, I know there's Fulvio, you are a torsion guy, but maybe you can address that question.
Okay. Yeah. So the main difference between the two is it's more geometrical than, let's say, in stress state. Well, first thing, all of them are shear deformation: rolling, plane strain, and torsion. All of them are plane strain deformation. So we have the deformation in two directions only. I think so that's why there's a very, well, these two are the preferred methods to simulate hot rolling. I think the plane strain compression, if you look sideways, we see that there's it's geometrically, it's very similar to rolling. If you have the two rolls, one at the top of the other and a strip in between, it's like you have the two plane strain compression anvils, in the two up and down, upside and downside of the specimen, and then you see that there's a very close geometrical similarity. It's not the same thing with torsion. You can imagine that, well, torsion, you can think that it's completely different, but in terms of stress state and strain, they're very similar to rolling. So they are both successfully used in simulating hot rolling. I can cover that in my next webinar, the TMCP, let's say in 3 or 4 weeks from now.
Great, thank you, Fulvio. And I think we have time for one more question. Again, there's a lot, and we will follow up. We will answer each of these questions and send out a kind of summary. We'll probably need to paraphrase some of them, maybe combine some of the questions, but we can do that probably in the next day or so. We get that out. There was a few questions about the Lumet. There's a question: does Lumet have a microscope already installed? I think maybe I can ask Brian Allen just to spend a couple of minutes. We're about out of time, but just to review again briefly how the Lumet does work. It does seem like it's a great opportunity to shorten testing time. But Brian, do you mind just addressing that briefly and maybe reviewing how, again, and Fulvio, maybe you can jump to those slides as well.
Sure.
Okay, yeah, absolutely. So the Lumet actually works by measures two things in the material. It measures the speed of sound in the material, and the speed of sound is calculated by the space between the echoes. So we know the dimensions of the sample, we know the time it takes for that shockwave pulse to go through the sample, echo off the back of the sample and come back to the surface. So that tells us the speed of sound in the material. Now, it turns out that the speed of sound actually gives us a lot of very useful information. The speed of sound is actually directly related to the bulk modulus of the sample, so you can imagine that you can certainly measure that. The speed of sound also can give us texture information because the speed of sound is actually going to be different in the different crystallographic directions of a sample. So for instance, if we had a single crystal sample, I would get a very different speed of sound depending on which direction through that crystal I measured the echo and the return. So that can give us information on annealing, because if say for instance, I have a sheet and I'm annealing that sheet, I can look at the texture change from the cold rolled texture to the fully annealed texture, and I can actually get information on that. The other thing that we get often from the Lumet is the grain size, and the grain size is actually can be related directly to we call it the decay envelope, or the reduction of energy of each echo. So the amount of energy that's scattered as that echo moves through the sample and back to the surface is directly related to the grain size. So we can actually make a correlation curve and understand what the grain size is based on the decay envelope of that echo. So there was a question, I believe, that asked if we could measure phase transformation during the Lumet. The answer there is absolutely yes, assuming that the phase transformation results in a different speed of sound. And obviously, a BCC is going to have a different speed of sound than an HCP or a FCC material. So typically a phase change will be accompanied by a very rapid change of the speed of sound of the material, and therefore the Lumet can pick that up very easily and very quickly. I think the original question actually talked about a microscope. There is no microscope in the Lumet, but part of the benefit of the Lumet is you don't really need a microscope, because if I can measure grain size, if I can see transformations that happen real time by using the Lumet output, then I don't really necessarily need a microscope, at least not for those measurements. I hope I got the answer to the question.
Thank you, Brian. Thank you. So we do want to be respectful of everyone's time, and unfortunately our time is up. But I do want to thank everyone for spending the past hour with us. We hope it's been valuable to you. I want to thank Fulvio for presenting, and our technical team. They've been busy responding to your questions. Again, we will summarize those questions and get them out to the group. If you do have technical questions about the operation of your Gleeble, please contact our service team. They may not be able to get on a plane and visit you or your Gleeble, but they are very good at providing remote support. The best way to contact our service team is to email service@gleeble.com to create a support ticket. We have a great new ticketing system to make sure we get back to you quickly. If you have questions about how Gleeble can support your research, please email me and I'll connect you with an application expert in your region or the right application expert based on your goals. My email address can be found in the invitation to this webinar. But in closing, please be on the lookout for a link to a survey so our team can continue to share information that you value. We'll also provide a link to download this presentation, as well as a link to view this video that may be coming out later today or early tomorrow. Again, I want to thank everyone for joining us. Please stay safe and healthy, and let us know how we can support you. Have a great day or evening.